In this video, we're going to be discussing a very useful tool for maximizing a quadratic form. It's known as the Courant Fischer formula for maximizing a quadratic form. Let's suppose that we have an n by n symmetric matrix A and it's positive definite. So recall that if a matrix is positive definite, that means all of its eigenvalues have to be positive. So let's order them lambda 1 greater than or equal to lambda 2, so on and so forth, up through lambda n. In other words, we're labeling eigenvalues in decreasing order, and the last one has to be positive. Now let's focus on the quadratic form, x transpose ax, where x is a vector in n space. And let's limit ourselves to vectors x whose length is 1. Now, depending upon what the vector is, the vector x is, this quadratic form will yield different values of scalars. What we want to do is we want to make this as large as possible, subject to the constraint that the mod of the absolute value, the length of x, is equal to 1. So how do we do that? Well, the Courant Fischer formula tells us that we set x to equal u, where u is the unit eigenvector corresponding to lambda 1. And in this case, the maximal value will be u transpose AU, which is lambda 1. So again, if we're trying to maximize this quadratic form where x is a vector of length 1, we can do so by looking at the eigenvalues, look at the largest eigenvalue, and find a corresponding eigenvector and normalize it. And that's what we can use to make this quantity as large as possible. Let's take a look at an example of that. Let's suppose that A is the matrix 7, 2, 2, 4. This is a symmetric matrix. It has two distinct eigenvalues, 8 and 3. This is a positive definite matrix, therefore, an eigenvector of 2, 1 and an eigenvector of minus 1, 2. The quadratic form x transpose AX, where x is a vector in two-dimensional space and it's 1 unit away from the origin, is largest when I let x be, let's look at the eigenvector corresponding to the largest eigenvalue. It's this eigenvector normalized. The length of this is root 5, so it would be 2 over root 5, 1 over root 5. So if I use this unit eigenvector, take its transpose times the original matrix A times the vector again, I actually get the largest eigenvalue, which is indeed 8. So if I choose any other vector whose length is 1 and the vector is in R2, and I substitute it in here into this quadratic formula, I am going to get something no larger than 8. Now, why does this work? This is a nice application of symmetric factorization. So A is symmetric. Let's assume that we can write it as Q D Q transpose. D is made up of the eigenvalues. I'm going to list them in decreasing order. They are all positive because A is assumed to be positive definite. The matrix Q has columns given by U1 up through UN. They form an orthonormal basis for Rn. We know that Q transpose times Q is the identity. In other words, Q transpose is the inverse of Q. Let's assume that x is a vector in n space and its length is 1. We're going to make a change of variable here. We're going to define y to be q transpose x. Now the length of y is the same as the length of q transpose x, but because of the nature of q, the length of q transpose x, q transpose is in essence a rotation matrix, so the length of q transpose x is the length of x, which we're assuming to be 1. So y is a unit vector as well. Let's take a look at x transpose AX. Replace A with Q D Q transpose. Now x transpose Q is the same as the transpose of Q transpose X, because if I took the transpose of this quantity, I would take the transpose of X times the transpose of Q. Here we have Q transpose X. Q transpose times X is just Y. So I have Y transpose dy. Now, D is a nice matrix. It's diagonal. So what we're going to do is we're going to replace y with a vector with its entries. So here's y1 up through yn, and here's the transpose of that. And then here's D, my matrix, which is diagonal with the eigenvalues along the diagonal. If I expand this, y1 through yn, and take the dot product with the first column there, I would get lambda 1. Lambda 1 times y1, actually. And then multiplied by that, I would get y1. It ends up that this product simplifies to be, and you can check this on your own, the sum from I equals 1 up to n, lambda I, y sub I squared. Now this term, this quantity, has to be greater than 0 because all of the lambdas are positive, and because y is a unit vector, it can't be a vector of length 0. It can't be the 0 vector. The way we can make this largest is that if we put everything in y1, so y1 is 1, the rest of the y sub i's are 0, so y would be just the unit vector 1 followed by a bunch of zeros. That's what would make this quantity as large as possible, in which case this would be just lambda 1. Now, if that's what y is, what does that say about x? X would be q times y. The reason is that if we multiply each side of this by q, x is qy, and q times q transpose is the identity. So x is qy. Here's q. The entries of q are those orthonormal eigenvectors. And then we have 1, 0, 0, 0, so on. And the only thing when I multiply this by this that's going to be left is u1. So when x is u1, that's going to make this quantity equal to lambda 1. There are various extensions of this theorem, but this is the simplest case. Here's an example for you to try. Find the unit vector in R4 that maximizes the quadratic form x transpose AX, where A is this matrix. I'll focus it just a little bit better for you. And then find the corresponding value of the quadratic form.